Symmetries play a central role in physics. A special class of symmetries that we are studying in the general theory of relativity are isometries, and they are symmetries that leave the metric invariant. Isometries can be generated by vector fields, which are called Killing vector fields, and when they exist, they play a very important role, and they are related to conserved quantities. We will also see that if we have such Killing vector fields on the manifolds, we can describe their symmetries from the algebra that they generate. So let's start by defining what we mean by an isometry. First, we should have a diffeomorphism from the manifold onto itself. And as you can see in this figure, through this diffeomorphism, a point P is mapped to a point Q. And let's have also two coordinate systems given by the charts U and V, so that the point P has coordinates x mu and the point Q has coordinates y alpha. Let us also have a metric on the manifold, and let's denote by g of x the metric at the point P, and by g of y the metric at the point Q. Let us use the map to pull back the metric from the point Q to the point P, and phi star g is this pullback. We have already seen that the components of the pullback metric are given in terms of the components of the metric at the point Q via this relation here. And for this to be computed, we need to know the y's as functions of x, and they are computed by the maps that are shown in this figure here. We say that this diffeomorphism is an isometry if the pullback metric at the point x is the same as the metric that we have chosen at the same point. That means, of course, that the components of the pullback metric and the components of the metric are equal one by one. Therefore, the equation that must be satisfied by this diffeomorphism is the one that says that the components of the pullback are equal to the components of the metric, and you see here that we have obtained a system of equations that is highly non-linear and difficult to solve. In order to study isometries, we consider isometries that are generated by the integral curves of vector fields, and we have seen that such diffeomorphisms define a one-parameter family of diffeomorphisms that are generated by those fields. So let's consider such a vector field and its integral curves, and let's pick such a curve that we assume that goes through both the points P and Q that we showed in the previous plot. So on this curve, the point P corresponds to the parameter t on the curve gamma, and the point Q to a neighboring point infinitesimally close to P, and it corresponds to the parameter t plus delta t. Then the coordinates of the point Q can be computed from the coordinates at the point P by performing a Taylor expansion, and we can consider the case where delta t is very small and approximate the new coordinates by keeping only terms to the desired order in delta t. So what we will do is we will consider an infinitesimal epsilon here, and in all our computations now we will ignore all terms of order epsilon square and above. Therefore, the coordinates y are equal to the coordinates x, and they are perturbed away from those values by epsilon times xi alpha, where xi alpha are the components of the vector field xi. So this relation gives us an approximation to those derivatives here, and they're easily computed to be equal to delta alpha mu plus epsilon d mu xi alpha. We can also Taylor expand the components of the metric around the point x and compute an approximation to the components at the point y, keeping also terms up to order epsilon here. And the expansion is done along the curve. So you see the d by dt derivative here. And if we write this derivative in this form here, then we see that g at y is equal to g at x plus epsilon xi lambda d lambda g alpha beta. We substitute this in the relation that must be satisfied if phi is an isometry, and now we will do some simple algebra, keeping terms only up to order epsilon. So you see the algebra is quite simple. First we multiply the two parentheses here, and then we take the result and multiply it with the leftmost parenthesis there. And in the end, if we ignore terms of order epsilon square, we have this expression that is of 0th order in epsilon and 1st order in epsilon here. Now, if you see, the terms of order epsilon are nothing but the components of the lead derivative of the metric in the direction of xi. So if phi is an isometry, then those left-hand sides and right-hand sides must be equal. The 0th order terms cancel, and therefore the 1st order term must be equal to 0. And this way we obtain a local condition that the metric should satisfy, and it is nothing that it is left invariant along the integral curves of the vector field xi. This should be no surprise. If we had just taken the definition of the lead derivative of the metric, we would have found the same result by this simple geometric formula. So notice now that we have obtained a local condition. It's a set of differential equations that need to be solved. And it is not necessary that such solutions actually exist. In fact, there are manifolds where such solutions do not exist and cannot exist. And such an example is, for example, if you take a compact manifold with negative scalar curvature, then there is no solution to those equations. Notice that we may find solutions in a coordinate system, but these could be just local solutions, and they cannot be extended to the whole manifold. We will see such an example later. Since we have written the condition that the metric should satisfy if xi is generating an isometry, it is very useful to prove this identity here. So let's assume that D is a Christoffel connection compatible with the metric and torsion free. And we write the first term, use the compatibility of the metric to raise the index inside the derivative, and then write down the covariant derivative of a vector field. Then use the fact that this is a Christoffel connection to substitute the Christoffel symbols by their expression that gives them in terms of the metric. And do a little bit of algebra. Notice that the multiplication of G with the inverse here gives Kronecker delta that will make all those indices here to be equal to nu, and we obtain this expression here. Now we have to compute the same thing with the order of indices on the left hand side reversed. All we have to do is to take the right hand side and exchange the role of mu and nu, and then we obtain this relation here. So you see nu here is substituted by mu, nu is nu, and similarly in this expression involving the metric here. Now we add those equations together. The left hand side will form the right hand side of the equation that we want to prove. Now there are many cancellations that occur here on the right hand side. You see that this term cancels this one, and this one cancels that one. So we are left only with this middle term, which is the same in both equations here. So we have twice 1/2 d rho g mu nu 0. And you see that this expression is nothing but the components of the Lie derivative of the metric with respect to xi in coordinate basis. So if xi is generating such an isometry, we call it a killing vector field. So a killing vector field satisfies the equation that its Lie derivative leaves the metric invariant. And as we have just seen, this is equivalent to saying that the symmetric part of d mu xi nu must be equal to 0. Notice if you have two killing vector fields on a manifold, then their commutator is also a killing vector field. And that means that killing vector fields form a closed algebra. That algebra is called the isometry algebra, and it generates the isometry group of the manifold. The reason why this property exists for killing vector fields is that the Lie derivative has the two properties shown here. The Lie derivative of a vector field with respect to xi is equal to the commutator of the two vector fields, and moreover, the Lie derivative with respect to the commutator of two vector fields on anything, not just on vector fields, is the same as the commutator of the two Lie derivatives acting on the same object. So if we compute the Lie derivative of the metric with respect to the commutator of two killing vector fields, that is the same as the commutator of the Lie derivatives acting on G. And then you see from the definition of the commutator that the result is equal to 0 because both He and Xi are killing vector fields and they leave the metric invariant. An easy way to find at least some of the vector fields, some of the killing vector fields of a manifold, is to choose a coordinate system such that the components of the metric in that coordinate system is independent with respect to one or more of the coordinates of that coordinate system. So let's say that there exists a coordinate system such that the components of the metric in that coordinate systems are such that they are independent of some of the coordinates, let's call it x sigma. So you see here in this figure that sigma are the coordinate lines for x sigma, and d sigma is the corresponding coordinate vector, and on the integral curves of that vector the metric is left invariant. So that means that in those coordinates, if you change x sigma to x sigma plus delta x sigma, the metric components here don't change. And that means that the partial derivatives of G mu nu with respect to x sigma vanish. then d sigma generates an isometry. Let's see why. From the coordinate system that we have just constructed, we see that the mu component of xi is just delta mu sigma. Therefore, the Lie derivative of the metric in the direction of xi has those three terms. That is true for any vector field. But now, if we substitute the values of the components, we see that the first term here has there is a Kronecker delta that will make this index here to be sigma, and the other two terms vanish because the components remain constant. So you see that the Lie derivative is just the partial derivative of g mu nu with respect to x sigma, and we have assumed that this is equal to 0. Therefore, d sigma generates an isometry. As we have already advertised, Killing vector fields are important because they are associated with conserved quantities along the motion of particles on geodesics. To see this, let's consider xi, which is assumed to be a Killing vector field. Here with blue we see its integral lines. So these are the ones that generate the isometries. And let's consider a geodesic with a fine parameter tau, and let's assume that its tangent vector is u here, which can be the values of a vector field on that curve. What we will see is that the inner product of u with xi remains constant as we move along the geodesic, which means that if we have xi, then we can have conserved quantities by forming the inner product of xi with the tangent vector of the geodesic. Of course, that means that the directional derivative of the inner product is 0, and we can write these equations in this form. Now that we have substituted with the covariant derivative here, we can apply the Leibniz rule and obtain those two terms here. And by rearranging a little bit the factors of each term, we obtain this. And we immediately see that the second term vanishes because gamma is a geodesic and tau is an affine parameter. Therefore, u du must be equal to 0. But the first term also vanishes, and the reason is because the product u nu u mu is symmetric under the exchange of the indices nu and mu. So we can replace d nu xi nu by its symmetric part. And by the Killing equation that is assumed to be satisfied by the Killing vector field, this is equal to 0, and the first term is also equal to 0. Therefore, this term here is conserved as we move along the geodesic. We can form other interesting conserved quantities by considering the stress energy tensor of matter fields. We haven't explained yet what this is, but all we need to know for the moment is that the stress energy tensor is symmetric with respect to the exchange of indices mu and nu, and that its divergence with respect to either index here vanishes. But this will give us no conservation law. But if there exists a Killing vector field, we will see that the current that is obtained by contracting the Killing vector field with the stress energy tensor is actually conserved. If we compute the divergence of this vector field, this current, then We substitute the definition here, and we apply the Leibniz rule. But the second term vanishes because of our assumption that d mu nu must vanish. But the first term also vanishes by the assumption that t mu nu is symmetric with respect to the exchange of indices mu and nu. So we can replace d mu xi nu here by its symmetric part, which vanishes due to the Killing equation. Therefore, the divergence of the current is zero, and we know that this leads to conservation laws. In fact, if Xi is time-like, we will see that this will enable us to define a conserved energy on the manifold. In fact, on space-like surfaces of the manifold. And if Xi is space-like, then we can have conserved momenta. But of course, there will be generalized momenta, like for example angular momentum, depending on the type of the coordinate that the space-like Killing vector will correspond to. So let's see in more detail the case where Xi is time-like. Let's consider a four-dimensional volume V such that it is bounded by two space-like surfaces, sigma 1 and sigma 2, and it extends up to the spatial infinity. Eta are the normal vectors to the two surfaces, and the direction is taken as shown in the figure. Then the integral of the divergence of J mu is by Stokes' theorem equal to the flux of J mu going outside the surface that is the boundary of the volume V. And the boundary of the volume V is nothing but the two space-like surfaces, sigma 1 and sigma 2, and the surfaces here that are found in spatial infinity. Now, notice here that there is a minus sign, and this is because we have chosen the normal to that surface to point inwards, whereas here it points outwards. The last term is assumed to vanish by considering matter fields such that the current here vanishes fast enough at infinity, at spatial infinity. Therefore, if the divergence of J mu vanishes, then this integral is equal to 0. Therefore, those two integrals over the surfaces sigma 2 and sigma 1 must be equal to each other. And this can be done for any volume V and for all space-like surfaces that can foliate space-time in such a way. So we have a conserved quantity, and we call this the energy on the space-like surface. And if we choose the Killing vector field to be the normal one to the surface, then the energy here is equal to the integral of J0, that is the volume element of the space-like surface. And by choosing the time coordinate to be given by the time-like vector field Xi, then this is nothing but the T00 component of the stress energy tensor. And the 00 component of the stress energy tensor is nothing but the energy density. So we understand why we call this quantity energy. And of course it is useful because it is conserved. Now, such a conservation law needs a time-like Killing vector field. So with a time-like Killing vector field, we have energy conservation. And that means that if we have static space-times, it is easy to define a global energy that is conserved. Now, let's try to understand what we have presented so far with some simple examples. Let's start with a two-dimensional sphere. We take the two-dimensional sphere with the usual metric given here, and the non-zero components are g theta theta and g phi phi, and they're given by 1 and sin squared theta respectively. The third line here is the Killing equation, and let's study it by considering all the possible non-trivial combinations of theta and phi. So let's start with having mi and ni to be theta and theta. So wherever we see mi, we put theta, and ni substituted with theta 2. And then when we sum over lambda here, we keep only the non-zero terms, and we notice that these are non-zero only whenever we have the diagonal components of the metric. Furthermore, g theta theta is 1, it's constant, so this term does not contribute to the equation, and all we are left with is g theta theta d theta xi theta. So this is the first equation that we obtain for the Killing vector field. The theta phi component is also obtained by putting the index mu to be theta and the index nu to be phi, and by keeping only non-zero terms, we have this equation here. Notice also that g theta phi is 0, so there's no derivative here for g. So if we substitute the values of the components of g, we have this equation here for xi phi and xi theta. Finally, the phi phi component of the Killing equation will give us this equation here, and by collecting only non-zero terms, we have this equation here. Now notice that g phi phi is sin squared theta, so this is non-constant with respect to theta, and this term will contribute to the equation. So we have the derivative of sin squared theta. And by doing some elementary algebra, we obtain this equation here. So we have obtained three non-trivial equations for the xi theta and xi phi components of the candidate Killing vector field. This one is the first one, the second one, and the third one. The solutions can easily be seen to be given by those expressions here who involve three arbitrary constants. You can convince yourselves that this is a solution by substituting to those three equations here. And now what we will try to do is to obtain three linearly independent solutions. So by choosing the parameters C1, C2, and C3 to be those triplets here, 0, 1, 0, 0, 0, 1, pi over 2, 0, 1, we obtain three different Killing vector fields which are linearly independent. Now don't be confused. The sphere might be two-dimensional, therefore the tangent space at each point has basis with two linearly independent vectors, but this is different than what we say here to be linearly independent. The linear independence condition here involves constants, and this equation must be valid at all points of the manifold, whereas the linear independence for basis is computed at each point and those real numbers at each tangent space become functions when you consider the whole manifold. So there's nothing crazy about having 3 linearly independent vector fields in a two-dimensional manifold. As you can see, the 3 vector fields, Xi1, Xi2, and Xi3, generate rotations on the sphere, and this is nothing but the group SO3. Now, let's consider conserved quantities, and let's compute them along a very simple geodesic, the one which is the equator theta equal pi over 2. So the tangent vector on the equator is just theta phi with components 0, 1 in the theta phi coordinate system. And then we know that the conserved quantity is the inner product of u with xi. And if you compute this, this is nothing but sin squared theta xi phi. And we have the xi phis of the 3 vector fields here. And we see that these are quantities that are kept constant as we move along the equator. Now, let's move on to another example. We consider the plane R2. Although this is simpler than the case of the sphere, it will give us an important lesson. So that's why we studied here in detail. So R2 is considered with the usual flat metric, which in Cartesian coordinates is given by this line element. And the Killing equation for the Killing vector field candidates is this one here. Now notice that the metric is both diagonal and constant. Therefore, the first term that involves the derivatives of the components of the metric is absent for all of them. So again, we start with the xx component of those equations, and we find that the x component of xi must be x independent. If we consider the xy component of this of those equations here, we find that dx xy must be minus dy xx. And the yy component gives us a similar equation to this one here, and it just states that xy must be y independent. So the solutions are easily computed. Since xx is x independent, it must be a function only of y, and xy must also be a function only of x. And the equation here tells us that the derivative of f must be minus the derivative of g. So we call those derivatives to be a constant c1, and the solution is easily computed and gives us the components of the family of all Killing vector fields with 3 arbitrary constants c1, c2, and c3. So again, we can compute 3 linearly independent Killing vector fields. If we choose c2 to be 1, then we have the vector 1, 0. Then if c3 is equal to 1, then we have the vector 0, 1. And if we take c1 equal to minus 1, then we have the vector minus yx. And notice that this vector here is nothing but the d phi coordinate vector of the rho d phi. So let's look at those solutions pictorially. So xi1 is the vector that points in the x direction and is the generator of translations in the direction of the x-axis. Similarly, xi2 is the generator of the translations in the direction of the y-axis, whereas x3 whereas Xc3 is the generator of rotations around the origin. So let's use those solutions to see what are the Killing vector fields on a cylinder. So the cylinder is going to be considered with the flat metric, same as that that we have on the full plane R2. But so in this case, it can be constructed by taking a strip of the R2 plane and identify two lines of constant y, let's say at y equal pi and at y equal minus pi. So that will give us a cylinder. And we see that by doing this construction, the Killing equations don't change. We follow the exact same steps as before, and we compute the same solutions in the xy coordinate system. The problem is that the xy coordinate system does not cover the whole cylinder. It covers the cylinder except this line here of the identification. But we see that the Killing vector fields Xc1 and Xc2 are well defined. And the way to see this is that if you take the limits as y goes to pi and as y goes to minus pi, the vector fields go continuously and differentiably to each other at y equals pi. And the same thing happens for Xc2. So Xc1 and Xc2 are globally defined, and you see here in a three-dimensional picture of the cylinder, they correspond to translations along the axis of the cylinder and along the compactified direction here. But you see that Xc3 is not globally defined anymore. Although it is locally defined, as we take the limits of y goes to plus or minus pi, we see that this limit is not well defined, and we obtain different answers by approaching this line from this direction or that direction. So rotations on the cylinder can be isometries only locally, but not globally. Another example that is useful to consider is the case of the Schwarzschild metric. This is the space-time around a spherically symmetric distribution of matter or around a static black hole. We have a coordinate system where t is a time-like coordinate and r, theta, phi are space-like coordinates. If we are very far in the so-called asymptotically flat part of space-time, then you see that r, theta, phi are nothing but spatial coordinates of flat space in spherical coordinates. But as we approach to the value of r equal to 2m, we have deviations away from this flatness. We notice immediately that all the components of the metric in this coordinate system are time independent. Therefore, there is a time-like Killing vector field which in those coordinates has components 1, 0, 0, 0. We also notice by inspection that all metric components are also phi independent. Therefore, the phi is also a Killing vector field, and its components in this coordinate system is 0, 0, 0, 1. There are no other obvious Killing vector fields because the other components of the metric are r and theta dependent. K, being a time-like Killing vector field, generates time translations, which are isometries, and we have seen that this leads to energy conservation. R is a space-like Killing vector field, generates phi translations, which correspond to rotations in the asymptotically flat space-time coordinate translations. So the conserved quantity will be an angular momentum. In order to compute those quantities, let's compute the components of the one forms obtained by lowering the indices of K and R. So since the metric now is non-trivial, those components are not 1 anymore. Let's also consider a geodesic with a fine parameter lambda. Then U du must be equal to 0, and the explicit components in this coordinate system is given by dt d lambda, dr d lambda, d theta d lambda, and d phi d lambda. So from what we have already said before, the inner product of K with U is a conserved quantity, and we call this quantity the energy of the particle. Whereas R dot U gives us another conserved quantity, which is the angular momentum of the particle. Now, if we have massive particles, then their 4 momenta is their mass times the 4 velocity. So actually in that case, what we have written here as E and L are energy or angular momentum per unit mass. In the case of photons, then what we usually do is we choose the affine parameter so that dx d lambda is the momentum of the photon. So in that case, we actually talk about energy and angular momentum. Now, let's now work out a simple exercise. If we have a Killing vector field, let us show that there's its second derivative with respect to a covariant derivative, which is a Christoffel covariant derivative, is proportional to the Riemann curvature tensor. In order to connect this twice derivation of Xi with R, we use the definition of the Riemann tensor that states that when we act with the commutator of 2 derivatives on Xi, we obtain Rxi. Now, for the first line here, we have written the equations for the indices mi ni lambda, which are the same as the ones that are required by the exercise. For the other terms, we write the first term here by cyclically permuting mi ni lambda in the positive way. So you have mi ni lambda, lambda mi ni lambda mi. The second term here is the same as the first one, with the first 2 indices reversed. And the one that involves the Riemann tensor has the 2 last indices here to be the same as the first term of the commutator of the derivatives. So it's mi ni here, it's lambda mi here, it's ni lambda there. Now the rest of the indices are easily placed. The index of the vector here is the first downstairs index of the Riemann tensor, and the other index must be contracted with Xi. Now what we do is we take equation 1 and 2 and add them together and then subtract equation 3. Let's see what we obtain from that. So let's compare the 2 yellow terms here, this one and that one. That will give us the first 2 terms on the left hand side. The second line has the green terms, this one and that one, with the minus sign here. And the last line has the red terms here, this one and that one, which will give those two terms here. Now for the right hand side, we take the first two terms that involve the Riemann tensor, with the indices here being lambda mi ni and ni lambda mi, and the third term here comes with the opposite sign because we subtract equation 3 and we leave it separate. Now there are many cancellations, and they come from the fact that Xi is a Killing vector field. So if we permute the indices mi and ni here, that are found here and there, because d lambda is the same, that will give us 0. And similarly for the second line here, d nu is common factor, and then we have mi lambda lambda mi, and that also gives us 0. For the right hand side, we have to use the symmetry of the Riemann tensor that says that its anti-symmetric part with respect to its three lower indices is equal to 0. So this sum here is equal to this here. So we substitute this there, and then for the first term, the yellow term, we also permute the indices lambda and nu, and we obtain an extra minus sign that makes this minus a plus. So you see here that those two terms are identical, so they're twice themselves, and the same thing happens on the right hand side. This and this are the same. So we see that we obtain the equation that we need to prove.